never panics, never complains, and never sues. But just like Jerry, we have patients worldwide that don't say anything when they need help. When he's lying in a hospital bed and something goes wrong, he can't call a nurse every single time. And also, we have to take in consideration nurse shortages worldwide.
Nurse to patient ratios have reached 1 to 8. That is a drastic increase from past years.
So, we, BioReact, have created a robotic system that not only monitors Jerry's vitals, but also acts when something goes wrong. We use an ESP32 microcontroller along with 3 potentiometers, temperature sensor, a fan, an LCD screen, and servo motors to control our system, which sends signals to our 24/7 live updating dashboard.
Now we use many vitals, and we use many medical principles to control those vitals. Firstly, we have SpO2, which is measured using a pulse oximeter. The pulse oximeter releases red light, as you can see over here. It releases red light, and depending on the amount of red light that is absorbed by the blood vessels, it can calculate the amount of oxygen in the blood. Secondly, we use bioimpedance analysis, which measures the conductivity of tissue to understand how much water is in the tissue. The more water that there is in the tissue, the more conductive it gets. We use GSR. Everyone can relate to the fact that when you get more stressed, your palms get sweaty, like how both of us are right now. Because of that, our palms get more conductive. GSR utilizes that fact and provides a measurable value over here.
So let's do a live demo to see what happens when Jerry becomes stressed. So stress potentiometer is right here. We increase it, and you can clearly see the tissue is flying above in the air. That means that the airflow has, we've turned on a fan because it's scientifically proven that with better airflow, your stress will reduce. And also, it's updating in real time. Now he's stable. Now let's see what happens when we make him dehydrated. So first, it updates.
Over here.
The next, our robotic arm gets ready to hand him a water bottle. Now, next, let's see what he does with the temperature. So we have a temperature sensor here, and when I put my hand on it, you can see that the temperature should be rapidly increasing. So let it update. A second. Yes, so you can see it's increasing, 24, now it's 25, and the fan is starting now, so we can balance his temperature out. Now, let's say we have Jerry feeling very cold. So I'm going to use bucket of cold water and dip it in here. His temperature is rapidly decreasing, and now we have an alert that his temperature is really low. Now our arm will work towards handing him a blanket for extending him comfort, because when you're cold you need a blanket.
These are meant to be temporary measures so that medical personnel can come and act on this, and so that the machine just does not beep and wait for something to happen.
That's why we have the dashboard as well. So after the robot is done acting to help out Jerry, we can have his family members looking out for him, his doctor. They're monitoring him in real time.
Now,
while we demonstrate SpO2, we'd like to talk a little bit about our challenges coming here. So, coming from a country where...
So it's up to you. You can go.
Coming from a country where we don't have accessibility to many components, so we try to include things like a camera, but unfortunately it's short-circuited, and that led to many problems. So we weren't able to include this as a feature. So our challenges, the fact that we were able to overcome these hurdles just means that anywhere, like lots of people in low-income countries, they don't have access to these healthcare systems, and we face similar challenges. We did not have access to these components, but still we managed to persevere, and we still managed to make up our system. So the fact that our system is complete, considering that we do not have accessibility to many components, just means that everyone worldwide using the system can use it. There's no implications with the cost. Actually, our unit only costs $300, whereas normal ICU grade monitoring machines cost thousands and thousands of dollars, denying healthcare access to lots of people in low-income countries.
We have made sure to make the profit margin as small as possible to ensure that everyone in the world gets this technology. Jerry thanks you.
We thank you. My name is Ira.
My name is Adishesh.
We are BioReact, and we're open to questions.
Thank you.
So you said sweat.
Yes.
How can it differentiate between sweat, excess sweat, and wet?
So sweat has a different chemical composition usually compared to normal water. Sweat has more salt in it. So we plan on advanced GSR systems use that fact as well to ensure that we can differentiate between actual wetness and just sweat in general.
How about wet as a blood, open wound?
Wet as blood, usually if that occurs, we were planning on putting a camera system. So as a preliminary measure, if there is a wound, we would immediately detect it and the medical personnel would ignore that warning. Secondly, blood does not have that much salt concentration compared to actual sweat. So that part is also negated by advanced GSR systems.
Thank you.
Thank you.
So I have one question. So currently what I see is like, it's pretty much reactive. So whenever these parameters are going beyond the threshold, then it is acting upon. So are you also planning to have it like, the predictive measures so that once you have those parameters in place, you will just predict rather than having it like, rather than having the reactive?
Yes, as a part of our original plan, we plan to include artificial intelligence, so it can definitely detect patterns in the vitals and it can warn the patients in advance. We think that's a very important feature that most old school systems lack today. So we want to work towards making sure everything is safer, making sure we have all the features to ensure that Jerry is not in any sort of trouble. So yes, definitely that is a feature that we are planning on adding.
Have you tried this on the real actual person?
So actually, it is practically ready for a real person. The only issue is the size, as you can see here, like none of us will fit into this chair. But I mean, all of the principles that we follow here are exactly the same as you have in a real person. We have potentiometers that change resistance, and resistance directly affects conductivity. So in a way, in real humans, we measure conductivity, and here we have potentiometers. They work on the same principles. So it's both ready for Jerry and ready for real humans just like us. The only thing that is not human ready is the SpO2 system. Since Jerry is cardboard, he doesn't have a blood flow, does he? So it was quite hard to simulate the SpO2 measuring system. So that's why we decided to stick to SpO2 with the potentiometer.
However, SpO2 is pretty easily measurable. These devices are accessible almost everywhere in the world. So that shouldn't be too much of a problem when we're actually implementing this in real life.
So when the vitals are critical, does it also send an alert to the actual nurses?
Yes, yes.
Over
so
here you can
let me demonstrate with the stress. You can see that it turns right.
Over here it turns red. So
So who has access to the dashboard?
We plan on including very high security encryption, so only permitted family members or doctors or friends of Jerry's can access his vitals. Oh, additionally, my apologies, I forgot to include one more feature, but our wheelchair can also move back and
forward, yes.
If I can just quickly start that.
It's also very important that we implement the cybersecurity measures on this specific feature, because if anything happens where he loses control of the wheelchair, it is extremely dangerous. So we're planning on implementing that also.
So he's not just stationary and stuck to one position, he can move wherever he likes.
So what is the central what is the central architecture that you're managing so many components together, right? So how are you managing that? What does your architecture look like?
So we have a lot of buck converters in the back.
To manage power.
Yes, so it ensures that the voltage does not go overboard, and unfortunately we have experienced that many times, as you guys can see. So learning from these lessons, we ensure that our architecture is very safe. There's no exposed electrical wires. We have taped every single little wiring piece with electrical tape just to ensure that there's good insulation. We use lithium-ion batteries, they're pretty stable, and just make sure that every single component is tied to a buck converter, so it ensures that the voltage does not go overboard.
And what code are you using on the back end?
We use C++, and for the EV, we use C++.
We use C++, and for the website we use JavaScript and HTML.
And CSS.
Yes.
Let us may come here to actually see the
It's really jam-packed with all this. It's as compact as possible to make sure it can be moved.
The project is a combination of the hand, chair, and all the things. $300 all the components.
So the original project itself, the wheelchair part of it, is $100 for our project. But we scaled it and increased cost for the wheelchair itself so that it can accommodate for larger sizes because no one is going to fit on this. That's how it reached up to $367 adding profit, everything should be accepted.
$367 is the selling price.
Yes, selling price.
So actually, just to be just for some clarification, that $367 is not for this seat, it's for the real actual thing.
The actual large wheelchair.
This I not even $40. It's really cheap. So $367 for the real person. Yes, that's
All of these have been scaled to include this.
And still we made them level parts or
We most likely use much more sturdy parts, obviously, like you can't handle damage. So yeah. What process will you guys?
Yes, please.
Just following up on that question of critical parameters, does it have any order to allow?
Currently, but we definitely think that's a really good addition.
I would like to add upon her point. We plan on making many different models. So one for ICU grade systems, one for house, for domestic use. In a domestic use situation, it wouldn't be as sensible to have like a giant alarm blaring every single time something goes wrong. So instead, we could differentiate based on different models.
Okay, thank you so much. Great
Thanks so
job.
much. Thank you.
Okay, now moving to the next team.
The camera is so that Jerry's friend, his family and his doctor can see him visually, not just looking at something. Yes.
Yeah.
Unfortunately, we could add it to short circuit. It's very Thank you so much.
Thank you so much.
Okay, next team. 6763-2. So just make sure about the team number when you use the rubric. Team name is Wow from Korea. Coach's name is An Ye-jin. Okay, are you ready? You have 4 minutes. Start.
Hello, we're Team WOW and our team number is 6763-2. WOW stands for Wearable, Optimal and Ways. I'm Chin Lee, our team's leader and software engineer, and he's our another software engineer,
Doing great.
and she's our hardware engineer, Linji Kim. We built a wearable EEG device named WOW that visualizes focus and mental state in real time.
ADHD isn't just about a lack of discipline. It is related to how the brain regulations of attention. However, diagnosis still relies on questionnaires and subjective observation. Other fields like construction sites, same monitoring, assembly lines, and hospital ICUs, and also need real-time mental state data. That's why we created WOW. On the hardware side, WOW measures photon load, EEG signals using three sensors. An EEG sensor for brain waves, a PPG sensor for heart rate, and ACC sensor for motion.
On the software side, our web dashboard receives the data over Bluetooth, filters noise, analyzes focus and stress, and visualizes the signal's quality and heart rate and motion in real time. Because it is browser-based, users can access it without using any software yet. Our biggest challenge was signal quality. At first, the signal was almost invisible because of the power line noise and motion artifacts. To solve this, we used a notch filter and a bandpass filter to get a cleaner signals.
Now let's see WOW in action. He's wearing the WOW device right now. At just 50 grams, it feels light and comfortable to wear. At the EEG tab, you can see the mental state, focus, stress, emotional stability, and signal quality in real time. Also, at the PPG tab, you can see the heart rate, SpO2, and HRV analysis with max and minimum. Lastly, at the ACC tab, it tracks the user's motion and the posture. Like this, if it moves, it changes the values instantly from the graph.
When we showed our prototype to parents and teachers of children with ADHD, they are most interested in seeing children's focus level in real numbers. Our first target is educational institutions and wellness centers, and we will start for B2B sales and then we'll expand it to B2C. For patent, we're filling applications for our EEG band design and focus analysis method and the visualization UI and real-time monitoring system. The total price is $40.2 and the retail price is $85. So WOW reaches about 53% margin.
WOW is lightweight, affordable,
30
and
seconds.
ready for commercialization. We are committed to creating a world where mental health is no more a mystery, but a data-driven reality. That concludes Team WOW's presentation. Thank you.
What is the interface between MCU and computer?
Can you say that?
The interface between MCU and computer?
Oh, the interface, this UI, we made it by ourselves and it gets the data from this and this sends to the data to this by the Bluetooth 5.0, yeah.
Like there's three sensors from that at that device. The EEG sensor and the PPG sensor and the ACC sensor. It gets the sampling rate by 500 Hz and 50 Hz and 25 Hz. So it's by Bluetooth 5.0, it sends the calculus results by the PCB board to the computer.
What is the ADC resolution? The analog to
ACC?
digital conversion resolution?
ACC resolution.
Yeah, how many bits?
By the, can you say the question again?
So we have the analog signal and that will be converting into digital and feeding to MCU, right? So there is a resolution between the real world and the computer bits. How many bits is that?
It is changing the rate by the 22.
Okay, let me ask you in a different way. So what is the size of the MCU, the registers?
The size of the MCU is the 500. And what was the next question?
The register, size of the register.
The size of the register is
When it's number of bits.
Okay, let me ask you some other question maybe while you think about that. So there are similar devices in the market, like Temple is one of those.
Yeah.
So how do you like envision people wearing band versus a small device?
There are many devices that measures brain waves, but the device is very cheap than other devices because we just use the EEG 2 channels. Even we use 2 channels for EEG, we can get a good
Results by
Yeah.
the 3 sensors. If there's only EEG sensor, we cannot get the accurate results. But if we have EEG sensor and the PPG sensor and the AC sensor, so like the total of the 3 sensors results, we can get more accurate sensors. And it is more reliable to take it at our hairband.
One follow-up question on that, as you mentioned, like you're using these sensors. You also mentioned about using Bluetooth, right? Now,
Yes.
if the Bluetooth is off and still like, you still have the ADC running on your head, let's say it turns off for 5 minutes, after it turns on after 5 minutes, does it still get all the data that was lost for the 5 minutes?
No, like we need to do the pairing again because
Okay.
if the Bluetooth 5.1 is off, we need the data gets reset. So we need to turn off the Bluetooth and turn on it again and pairing with this connected device.
Okay. So it can be also like you can have it on your phones as well, right? Like,
Yeah, if we have this dashboard URL, you can send it to other phone or other computer and go into this dashboard.
okay.
Can I see the band?
Yes, of course.
Can you show that band?
Okay, this is our band, and this yellow parts are EEG signals, and this shoots the data, and then it goes back. So the EEG sensor, the EEG sensor sends the bands, the data, and this is the PPG sensor, and ACC sensor, the calculates the degrees, so it's in this part.
At here there is our ICC sensor and the battery, lithium battery at here, and this is the Bluetooth connecting button. Like this. Here's the sensors and here's the battery and the board. You see.
Did you purchase? What did you purchase, and how did you make whole band?
First we made the sensors and the board together, and with the silicon band we thought it need to be attached to our head, and not if we move it need to it doesn't have to got it off. So we used the silicon band and we bought these sensors as the device mount.
And does it also measure cognitive load?
Excuse me?
Does it measure cognitive load on your system, on your brain?
Yeah. Can you say it
So
with easier
you
words?
mentioned like cognitive load, meaning like the mental state, right?
Yes,
The stress
yes,
level.
yes, yes,
Does it
focus.
measure that?
Yes,
it's
like
measures.
at the EEG sensor you can get the rates of the emotional stability, focus and stress and total powers, etc. Like this is like pick off our head, so there's 0, 0, 0, 0, 0. But if we put it to here, like like for example, emotional stability is the total plus alpha plus gamma, and like that we can calculate the data. These data are from the other neurosync and bio we have.
Okay, thank you.
Can I test it?
Oh, yes.
Can you check my stress level?
Yeah.
Oh my gosh. We're gonna be stressed out just seeing the output we're getting.
Oh, okay.
Yes. Fast procedure, oh my God.
Yeah, explain, the data shown here.
Like, usually for the